Welcome to this second video of my playlist about the preparation of alkynes. In this presentation I'll show you some strategies for alkylating terminal alkynes, that is alkynes with an sp-CH bond. Most reported examples of such alkylations were conducted under alkaline or neutral reaction conditions. Typically, the alkyne is first metallated, either partially or completely, and then treated with some carbon electrophile. Typical alkylating reagents include alkyl halides, epoxides, ketones, imines, or electron-deficient olefins. I'll show you specific examples in a minute. Examples have also been reported of alkyne alkylations under acidic conditions. These include Mannich-type aminoalkylations with iminium salts and related alkoxy alkylations with acetals. Let's check some specific examples. Here, lithiated acetylene was alkylated with a primary alkyl chloride. Because unactivated alkyl chlorides are unreactive, the reaction required addition of DMPU as dipolar aprotic solvent and heating to 52 degrees Celsius for 11 hours. Alkylation of acetylene was faster than ether formation by alkylation of the alkoxide. Secondary alkyl chlorides are still less reactive, and in this example, catalysis by nickel, copper, and iodide was required. The alkylation was conducted in DMSO, which is particularly well suited for sluggish nucleophilic substitutions. I want to mention already now one important side reaction: the copper-catalyzed oxidative dimerization of terminal alkynes, the so-called Glaser or Eglinton reaction. This dimerization usually requires oxygen and is fast and difficult to suppress completely. It should always be kept in mind when performing copper-catalyzed alkyne chemistry. Then, some transition metal complexes catalyze the non-oxidative dimerization of terminal alkynes. These reactions are discussed in part 4 of this video playlist. This is another example of catalyzed alkylation with an alkyl chloride, similar to the previous one. In this instance, dioxane could be used, but strong heating was required. The aryl bromide remained unchanged. Benzylic chlorides are more reactive than simple aliphatic chlorides and cannot undergo beta elimination. Here, 1-hexyne was alkylated with a particularly reactive benzylic chloride. Large amounts of copper iodide, tetrabutylammonium iodide, and potassium carbonate were used, but it is unclear if such excess of reagents was really required. Allylic chlorides are also more reactive than unactivated alkyl chlorides. In this example, methylbutinol was allylated with a substituted allyl chloride. Catalytic copper iodide and an excess of triethylamine brought about a complete conversion after 28 hours at 50 degrees Celsius. No additional solvent was required, and the alkyne added exclusively to the terminal methylene group without any formation of ethers. Even benzylic ammonium salts can alkylate terminal alkynes. Here such a reaction was catalyzed by palladium zero alone, without any copper salts. Despite the high reaction temperature, the product did not isomerize to an alene or diene. This is an example of alkyne alkylation with an alkyl bromide. The alkyne was metallated stoichiometrically with sodium amide in liquid ammonia. The yield wasn't high, probably because of the difficult dosing of propyne. Here, propargyl alcohol was alkylated at carbon with a primary alkyl bromide after twofold lithiation with lithium amide. No ether was formed. Because of the acidifying effect of sp carbon hybrids, terminal alkynes such as hexyne can be converted into dianions. These react with electrophiles first at the propargylic position and then at the terminal carbon atom. This enables selective sequential alkylations, as in this example. Here an alkyne was again alkylated without stoichiometric deprotonation, just by stirring with an excess of a tertiary amine and 1% of a palladium catalyst. The yield of benzylated alkyne was excellent. In this example, an alkyne had to be alkylated with a secondary alkyl iodide. Complete deprotonation with isopropyl magnesium chloride and iron catalysis in DMF provided the target product in high yield. Trifluoroethyl halides or sulfonates, like the electrophile of this example, are exceedingly unreactive. Sometimes it is almost impossible to perform nucleophilic substitutions at these substrates. Here, however, the authors succeeded in trifluoroethylating a terminal alkyne with the aid of a palladium catalyst. Surprisingly, no quaternization of Dabco occurred. Dabco is not a convenient base for alkylations because of its high nucleophilicity. Dabco is even quaternized by dichloromethane within minutes at room temperature. This is a rather weird strategy of alkylating alkynes with the aid of a diazonium salt. According to the authors, this salt acted as a source of mesotyl radicals, which in turn abstracted iodine atoms from the electrophile and thereby generated a secondary copper-stabilized alkyl radical. Still, as I showed you on a previous slide, secondary alkyl iodides can alkylate alkynes in high yield, even without oxidants. Epoxides are similarly reactive as alkyl bromides or chlorides and can also be used to alkylate alkynes. The regioselectivity of these reactions is difficult to predict correctly, though. In this example, a lithiated alkyne was alkylated with a styrene oxide in a mixture of THF and DMSO. Clean nucleophilic attack at the methylene group of the epoxide occurred. Some types of allylic alcohol can be used directly as electrophiles without further activation. In this instance, the allylic alcohol, prepared by a Baylis-Hillman reaction, was also a good Michael acceptor and thus a good electrophile. Alkylation of an alkyne succeeded with the aid of a palladium catalyst under essentially neutral reaction conditions. In this example, phenylacetylene was alkylated with an enol ether under slightly acidic conditions. With the aid of a copper catalyst and catalytic vitamin C as reducing agent, the electrophile underwent stereoselective allylic displacement of the acetate group. A particularly relevant reaction is the hydroxymethylation of acetylene with formaldehyde. Depending on the precise conditions, either propyl alcohol or butenediol is obtained as main product. In this example, the alkylation was conducted under pressure in aqueous THF with copper acetylide and supported bismuth oxide as catalysts. The conditions were slightly acidic. With iminium salts and chiral copper complexes, enantioselective alkylations of alkynes are possible. In this example, the iminium salt was formed from dibenzylamine and an aldehyde. With just 5% of catalyst, an enantiomerically enriched amine was obtained in high yield. Also, pyridinium salts can be used to alkylate alkynes enantioselectively. In this instance, high enantioselectivities could only be achieved with acceptor-substituted alkynes, but not with simple aliphatic alkynes. In the presence of certain catalysts, enamines behave like iminium salts and act as electrophilic alkylating reagents. In this example, silylated acetylene was aminoalkylated enantioselectively with an acylated enamine. The reaction was catalyzed with 5% of a rhodium complex. Ketones are less reactive than aldehydes or aldehyde-derived iminium salts, but can still react with only partially metallated alkynes. Here, a ketone reacted with acetylene in liquid ammonia with just catalytic amounts of aqueous potassium hydroxide as base. In this example, a ketone with an additional electrophilic site cleanly reacted with lithiated acetylene at the carbonyl group. Alpha-beta unsaturated ketones are also good Michael acceptors and occasionally undergo Michael addition, even without copper or other transition metal catalysts, but this did not happen here. By adding enantiomerically pure amino alcohols to such alkylations, enantiomerically enriched propargylic alcohols can sometimes be obtained. Here, an intermediate for the manufacture of the antiviral drug efavirenz was prepared this way, but the procedure was quite complex. Anyway, a high yield of the tertiary alcohol was obtained with 96% enantiomeric excess. Norbornenes and norbornadiene are particularly reactive because of ring strain. In this example, norbornadiene could be alkenylated with a terminal alkyne and a palladium catalyst. A competing reaction was the dimerization of the alkyne, but this could be prevented here with an excess of norbornadiene. Simple Michael additions of alkynes can also be catalyzed by palladium or copper complexes. In this example, a palladium-catalyzed Michael addition succeeded in a biphasic mixture of water and toluene, without any acid or base. Instances of enantioselective Michael additions have also been reported. Here, a chiral rhodium complex was the catalyst and the Michael acceptor was a substituted nitrostyrene. This here is a recent example of the alkylation of a copper acetylide with carbon-centered radicals. In the presence of a quinine-derived enantiomerically pure ligand, the alkylation proceeded with high enantioselectivity. This is an interesting example of the direct use of calcium carbide as acetylene source. Under strongly alkaline conditions, a single alkylation of acetylene with a tosyl hydrazone could be achieved. As I discuss in part 6 of this playlist, alkynes readily isomerize when treated with strong bases. Because of the large amount of potassium terzbutoxide used here, the result depended on the precise structure of the product. In the case of acetophenone-derived hydrazones, allenes were mostly obtained. I've sketched here one possible way by which sulfonyl hydrazones can alkylate carbon nucleophiles. This is an example of alkyne alkylation with triethyl orthoformate. Such reactions generally require Lewis acid catalysis, and here 2% of zinc iodide or nitrate could be used. Despite the high reaction temperature, no addition of ethanol to the alkyne or alkylations with the acetyl occurred. As mentioned above, carbon-centered radicals can react with alkenyl copper complexes to yield alkylated alkynes. Here, a terminal alkyne was trifluoromethylated with an excess of bis-trifluoromethyl copper at room temperature in DMF. The radicals were generated by oxidation with air. The copper reagent was prepared from fluoroform and copper chloride, as shown here, as a solution in DMF. Metallated alkynes can also be generated in situ by beta elimination, as discussed in part 1 of this playlist. Here, for instance, a lithiated alkyne was generated from a 1,2-dibromide, and alkylation with an aldehyde yielded a propagyllic alcohol directly. In this example, a lithiated alkyne was generated from a vinylidene dibromide, either by beta elimination and reduction or by bromine-lithium exchange, alpha elimination and rearrangement. Addition of paraformaldehyde then gave the primary alcohol. Here, a trifluoroethyl acetyl was converted into an alkoxyalkyne by a sequence of dehydrofluorinations and a Michael addition of butyllithium to an intermediate olefin. Unprotected 1-hydroxyalkynes are unstable and would tautomerize to ketenes, but protected hydroxyalkynes, like the product of this synthesis, are similarly stable as enol ethers or ketene acetyls. This example is similar to the previous one. Reductive elimination yielded an intermediate 1-chloroalkyne which underwent chloride displacement with methyl cuprate. So, what can go wrong? I've already mentioned some of the many potential side reactions, like the oxidative dimerization of alkynes. Transition metal catalyzed reactions with terminal alkynes should always be carefully degassed, and the products should be analyzed for possible alkyne dimers, which can be explosive. Then, because of the electrophilicity of alkynes, nucleophiles such as cyanide, amines, alcohols and thiols can readily add to the product. Strong bases can isomerize alkynes to other alkynes, allenes, or conjugated dienes. This will be discussed in part 6 of this playlist. The base-mediated addition of alkynes to ketones or imines is reversible, and propagyllic alcohols and amines can sometimes be cleaved again, as in this example. The starting alcohol of this reaction is therefore a convenient protected form of acetylene. This alcohol can, for instance, be arylated or vinylated at the acetylenic CH group, and afterwards acetone can be cleaved off by treatment with a base. Intramolecular nucleophilic additions to alkynes are particularly fast and can sometimes be difficult to suppress. Here, aminoalkylation of a substituted phenylacetylene under almost neutral conditions did not yield the expected alkyne but an indole instead. Here's a selection of some further examples, which you can also find in the description of this video. Under the Community tab of my channel, there is a downloadable PDF version of the slides. The next video of this playlist is about the arylation of terminal alkynes. There you can find examples of Sonogashira arylations and a number of variations of this chemistry. See you then!